Okay, we're ready to head off into the numerical solution of this item, where we've got then a support movement that happens at B. We've got two spans with loads on them. We have different span lengths, and we also have different bending rigidities that go along with this. All right, so we've already begun to set up the table that goes along with the moment distribution calculation. We've got I over 5 for the two outer spans. We have 2I over 7.5 for the middle spans, or middle span. And so if we rewrite that real quick using a common denominator approach, that'll be 3I over 15. This will be 4I over 15, and that helps us then realize that a total stiffness coming into joint B is 3 plus 4 or 7, so the distribution factor for that left-hand span is 3/7 at joint B. For the middle span of joint B, that will be, of course, the complement to get up to 1. And we have a mirror image type of situation over here at joint C. Same kind of thing. We're never going to release joint A, and we're never going to release joint D. Right now, the support movement effects we already have calculated out as being the minus 72 kilonewton meters. Let's put that unit over there to remind ourselves what we've got. That's what we've got over here at the left, but we do need to get the fixed end moments here for the applied member load. And remember that with a fixed beam and a uniformly distributed load of W, that our fixed end moments are going to end up being WL squared over 12, one being one direction at one end, and of course one at the other direction at the other end. So now we can of course go 80 times our span length of 5 squared. It's 25 divided by the 12, and of course that's 166.67, negative on the left and positive on the right. Notice we haven't released any joints. Everything is locked down right now, so that's going to just mean that our total moments are just additive here. The middle span doesn't have an applied load, so those are 0. We go to the far right span, and it's still WL squared over 12. It is still, well, the only thing that's changed is that it's 100 instead of 80, so we can then just scale that up to 208.3. Now recognize too that you could have introduced some small error by just going to the nearest kilonewton per meter and not really affecting, from an engineering standpoint, the results all that much. And sometimes I do get a little, it's not really lazy, I just don't like carrying too many digits in these calculations, because it gets kind of cramped and it doesn't really have a big picture effect at the end of the day. Alright, so let's get going here. What I do is I try to find the joint that seems to have the largest unbalance before I do anything. This is 208, a negative, and a 64 here, which is, roughly speaking, right around negative 140. This has got a, let's see, that'll have a net of about negative 8. So they're kind of the same. It looks like this one might be just slightly bigger, so it doesn't matter, of course. It might speed up the pace at which you converge in your answer, but it's not going to really have that much of an effect. 166 point, this really was 6 repeating, even though I don't really need that. Sometimes, because I can keep this in my calculator, I will go ahead and include that greater precision even if I don't write it down that way. There's our net unbalance at that joint. We of course are going to have equilibrium by when we release it, developing the opposite of that. And we'll take that times 3 divided by 7, and that's a minus 68 even in response. And that'll get carried over at half to minus 34. And then we've got our unbalance times 4/7 to go to the other side of the joint. Make sure that I show that that has been equilibrated. You do that out of convenience so that you can keep track of what you've been doing. Carryover effect of minus 45.3, and then at that joint, then we haven't released it yet, so we have accumulation of all of this plus 64 minus the 208.33333, and that's a minus 189.6. Again, take the opposite of that, drop it in, take it times 3 divided by 7, and so that's 81.3 positive. Divide that by 2 for a carryover, and forgot my little arrow over here. Don't have to have arrows, it's just really helpful to keep track of what you've done. Go back to that unbalance at that joint, times 3 divided by 7, oops, that's not right, times 4 divided by 7, that's 108.4 positive. See, if we added up everything at that joint right now, it should now equal 0. We'll shoot across half. So 54.2 is positive. We don't have anything coming back to us from the fixed end at the far left because we're never going to release that. So we can go ahead and deal with that one at B right now. Take the opposite of it, times 3 divided by 7 equals minus 23.2. Immediately take half of it, minus 11.6. Piling up a lot of negative over here on the far left, but that's the way it goes. Go back to here, times 4 divided by 7, and we're at 30.96. Now this is always an interesting question. Do you round that to 30.9? Do you round it to 31? And I'm going to round it to 31 because then it'll look like I have that 54.2. I'm keeping all this actually in the calculator, so at some level you could say it's not such a big deal, but it'll matter later just slightly, not really, when we add up these columns. And you know, from here this is all just same old calculation every single time, or at least the process is. I don't know if you've picked up on how I'm always doing the outer spans first. It's just kind of a convenience factor about how what's stored in my calculator and the pattern of what's going to happen and dividing by 2 and what's easy to do. You'll pick up on some of these rhythms yourself. Looks like here I might have made a slight little rounding error. Let's go back, times 3 divided by 7, 6.6. Yeah, you know, sometimes I'll write this as 8.9 just so that those two add up to be what we know they're supposed to really add up to. 8.8. Well, I just don't really want to round that up, so I'm not going to. So there's a little, at least on the page, I just introduced a little bit of rounding error. Notice how fast this is coming down in terms of the overall magnitude. This is going reasonably quickly. Times 3 divided by 7, 1.9 divided by 2, and that times 4 divided by 7, 2.5. Notice too that because that middle span is stiffer, it's keeping more of this unbalanced moment in the middle, which means it's taking us slightly longer to go. If these had been flip-flopped, more of this moment would have gotten sucked over to the outside, and this would have actually converged a little bit faster as we went down along the way. Don't know if you can see that number, minus Yeah, we're really starting to get into rounding error in terms of writing things down. But again, it's going pretty fast. Times 3 divided by 7. And when you're in this pattern 2, note that you should expect to see that the pattern of the pluses and minuses when you're following a regular pattern should be the same. So it's easier to pick up on that you may have made a mistake on plus and minuses just because of that pattern that begins to emerge. We're going to get another one where it's not going to quite add up to that right value, but because I'm keeping the fuller digits in my calculator, I'm going to just go ahead and write it down the way it shows up. That's always an interesting question of what should you really do there. And of course you could keep more digits, but notice these errors are that I'm effectively writing down are errors that should randomly kind of balance each other out, and they're way out there at a level of practical aspect that should not have any sort of impact on real design or real performance. And we're really getting down low here. This one now amounts to being a 0.15, and see, now we really have sort of a theoretical rounding error problem, because I'm going to get to there with a minus 0.2, and we're so small I'm going to call that done. I'm not even going to shoot this half of the 0.1 over, because it's not going to have any sort of impact on anything. I'm just going to call this a day. When I get to that final thing, I always do the double line. Now we get to just add up all those columns and see how close we really came. These are all negative values, so 72 plus 166.7 plus 34 plus 11.6 plus 0.9 equals 285.2, all negative. Over here we have a negative 72 plus the 166.7 minus 68 minus 23.2 minus 1.9 minus 0.1, and we get a net of 1.5. It's interesting. Very small, close to 0. That's effectively the impact of that support movement. 64 minus 90.7 plus 54.2 minus 31 plus 4.4 minus 2.5 plus 0.4 minus 0.2, and we get a negative 1.4. So that's essentially the same, and we know that we made a couple of little small things. These two don't add up quite the way they really ought to. We know that that was a 0.15. That's probably a 0.25-ish, and so we're not expecting that to be exactly perfect just because of that mistake that rounding error that we know we've introduced the way we've written it down. This is really ideal for doing spreadsheets, and you'd of course be able to keep a lot more precision, and you'd feel better about it. Engineering wise, you really wouldn't have any change in your answer. I've said that like 4 times probably by now. I hope you're picking up on the difference between that mathematical accuracy and the net effect in any sort of real performance side of things. It's not an excuse to be sloppy, it's just saying pick and choose where you want to be super precise at. Here's another one where we're 0.1 off here, and we know for sure there's a 0.1 difference here, a 0.1 difference there, and so it's not really surprising at all that we even have a 0.1 difference in effect up in there too, that it flip-flop back and forth in terms of its impact. And then the last one, and 252.5 positive. Alright, so those are the member and moments. Let's go back then and actually draw shear and moment diagrams. We'll do that in the next part.